We have just met the basis pursuit as a way to approximate the solution of P0 epsilon. We turn to present a specific numerical algorithm that aims to solve the basis pursuit goal, the IRLS, iterative reweighted least squares. Yes, we have met this idea before, and now we will refine it to a new goal. This is the basis pursuit goal, finding the shortest vector x in L1 norm such that AX is up to epsilon away from B. In many circumstances, we will find it more convenient to replace the constraint by a penalty, getting what we refer to as the Lagrangian form. The above two formulations are equivalent in the sense that for every epsilon in the first, there exists a lambda in the second such that the two lead to the same solution. However, on the downside, this match between epsilon and lambda depends on A and B. Still, we will work with the Lagrangian form and later discuss a way to get the solution of the constraint problem from it. So, how does the IRLS work? By modifying the L1 into an L2 norm. The L1 norm of x is the sum of its absolute entries. This could be rewritten as a weighted sum of the squares of the vector entries, where the weights themselves are the reciprocals of the entries. Observe that we added a factor of half in front of the expression and a 2 inside each of the weights accordingly. The reason for this will be made clear in a minute. Let's define a diagonal matrix W of x containing these values on its main diagonal. And so, L1 has been turned into a weighted L2 norm expression. The key idea of the IRLS is to consider W as fixed and solve the problem for x. Then update W based on the obtained solution. Iterating between these two steps is the IRLS algorithm. Here is the IRLS in slightly more details. Let's start by assuming that W is fixed and the L1 has been replaced by this expression. The resulting problem is a simple quadratic penalty, and its solution is easily obtained as a solution of a linear system. The factor half that was introduced earlier simply makes the linear system more pleasant to read. Given the just computed x, we go and update the matrix W. This is the resulting W, a diagonal matrix of a simple form. Observe that we added a small positive value delta to each denominator in order to assure that we do not divide by zeros. Here is the IRLS with all its details. We initialize the algorithm with a vector of 1s and apply a series of the following iterations. In each iteration, we first compute the weight matrix based on the currently available x, and then we update x based on the linear system we have seen. The algorithm proceeds as long as we see a sufficient update to the solution x. This is a very simple algorithm, easy to implement, and this explains its appeal. Here are a few important observations regarding this algorithm. First, solving the linear system for updating x might be prohibitive, and especially so for high-dimensional problems. This can be mitigated by applying few steps of steepest descent or conjugate gradient. This means that we will only approximate the solution of the linear system instead of getting its exact solution. Another important feature to be aware of is the fact that this simple algorithm comes with no theoretical guarantees for the quality of solution it leads to. While performing nice in practice, we cannot claim that we get the optimal solution. Indeed, we cannot even claim that the Lagrangian penalty function is monotonically decreasing as this algorithm iterates. I'm sure you have noticed that our initialization was a bit strange, choosing x0 to be a vector of 1s. Why? Well, remember that immediately after the initialization, we compute the weight matrix W. If we would have started with zeros, this W would have been the identity matrix multiplied by 1 over delta. This would have stalled the algorithm since this penalty is too aggressive. By starting with 1s, the algorithm gets a more relaxed starting weight matrix that enables a faster convergence. Still on the same matter, observe that if at some point of the algorithm a specific entry becomes 0, its corresponding weight becomes 1 over delta, which is quite large. This means that we heavily penalize its value for later iterations, and thus its chances to get back to a non-zero value are very slim. So, put in simple terms, when an entry in x becomes 0, it is likely to stay this way all through the algorithm. Sometimes the IRLS is too violent and tends to diverge. In such a case, we need to slow it down, and this can be done by updating x, as we have already mentioned, applying few iterations of steepest descent. Another way to relax the algorithm is to compute a weighted average of the previous solution and the new one, as shown here. If alpha is chosen as 1, we come back to the regular IRLS. And as alpha tends to 0, we slow the iterates more and more. What if our goal is the constraint problem, P1 epsilon, and not its Lagrangian form? Then we should apply the IRLS for varying values of lambda and search for the lambda that meets the constraint that AX is epsilon away from B. In doing so, note that there is a comfortable rule that ties lambda to epsilon. When lambda grows, so does the error between AX and B. Thus, a bisection algorithm makes much sense in this case. Also, we can always initialize one instance of the IRLS with the solution of another one. In other words, warm start.